Hello and welcome to our review of AP Calculus. We have 3 weeks until the test, and we're going to take this time to brush up on some of the skills that we haven't used since, beginning of the year, and see how it kind of fits into what we're doing now. So this week we're going to concentrate on limits, derivatives, and integrals, just the basic stuff to keep that going in our brain. And then next week we're going to take specific free response problems from previous tests and examine those. By the time you get that test on May 12th, I hope you'll have seen the types of questions that you'll be given and know how to handle them. It's not that the AP test is necessarily a difficult test, it's just sometimes the questions are asked in a strange way. So that's what we're going to concentrate on next week, but just a refresher of skills. So limits and continuity, really the building blocks of calculus. Everything we do with derivatives and integrals is based upon a limit as something goes to infinity. So just the idea of a limit, we're going to study again. So remember, the basic idea of a limit is where a function is going. It doesn't have to get there, it just has to be going there. So the first thing you always do is you just plug in the value. We're going to plug in -3, and we're going to see what we get. So that's 9, it's -18 plus 1, which is -17. So the function actually equals -17 at -3, but that's also the limit. The limit is where it is going. Okay. Now in this case, and we do the same thing. We first always plug in the x value and see what we get. So we're going to have a -1 squared. Oops, excuse me. 2 times -1. Plus 3, all of that over -1 squared plus 1. I can already tell you it's going to be an okay problem with not much to do because that bottom is going to be not 0. Remember, when the denominator is 0, that's where we have issues. If both the numerator and denominator are 0, that means that we have more steps to find the answer. All right, so let's see what we got. So -1 squared is 1. Right? 2 times -1 is -2 plus 3. So this is 1 plus 3 is 4. 4 minus 2 is 2. Well, that becomes 1. Just like that, no big deal. Just plug in the number. Now visually, what does the limit mean? So this is the graph of this piecewise function. And the question is, what's the limit as x approaches 1? So remember, x approaches 1 along the x value. That's where the point is approaching as the x values get closer. Or think of it this way. As I slide along the x values and from both directions, where am I going? So the limit is where you're going. The actual point is 1, 1. That's the point that exists. But I don't care about what exists and doesn't exist. Where is it going? And it's going right here, which is the x value of 2. So where is it going? It's going toward 2. The limit is 2 as x approaches 1. All right. This one, plug in 1 again. This was actually an error. I have to apologize for this. If you got a little, say, where did the answer go? And plugging in 1, right? 1 squared is 1. 1 plus 1 is 2. So your answer is 1 over the root of 2. And no matter if you rationalize or what, you see it's not here. So none of these answers are correct. I believe C was meant to be the correct answer, but let's make this letter F, and we'll call it 1 over the root of 2, and we'll say that's the answer. What do you think of that? Okay. And for those of you that must rationalize, because I understand, I feel the urge to do this myself, but it's not always a necessary step. Just know if you need to know how to do it, that's what you do. All right, number 5. What is not true about this graph? So what do you think? You don't necessarily need to know what the graph looks like, but let's look at these ideas one at a time, and we'll go with that. F is continuous at x equals 10. So continuous means there's no break. So if I plug in 10, I get 10 squared, which is 100, minus 25. The square root of 75. That's looking fine. That's true. So that can't be the answer. F is continuous on the interval negative infinity to negative 5. All right, so anything less than negative 5. So what happens at negative 5? So at negative 5, all right, negative 5 squared is 25. 25 minus 25 is 0. So it's okay for it to equal 0. All right, so that part's okay. It can equal 0. What about anything less than that? Well, let's just pick a point. Let's pick, not a value, let's pick a value. Let's pick negative 6. Why not, right? So negative 6 squared minus 25, which is, what's that, 36 minus 25. That's the square root of 11. That exists. So this is true. Can't be the right answer. Is this continuous on 5 to infinity? Well, I think we'll find the same thing if we plug it in here. If I plug in a 5, then I'm going to get 25. Whoops, I'm sorry, that's not right. Oh, that was right. Okay. If I plug in 5, I'll get 25 minus 25. So it definitely can equal 0. So that hard bracket is good. Now, any number greater than 5. So let's choose 6. And you notice it's going to be the same thing. 6 squared and negative 6 squared are the same thing. All right, so you're going to get 36 minus 25, which is a perfectly fine number. That is true. So that can't be the right answer. F is continuous between negative 5 and 5. And here's where we have the problem. So pick a nice value between those two, like 0. What's f of 0? Well, we'd have 0 minus 25. And we're only dealing with real numbers. So guess what? It's not continuous there. This statement is false, so that is our correct answer. And you're going to find out that E, we just showed, E is true. F is not continuous at 0. So D is the correct answer for number 5. Okay. If I plug in 0, the first thing you should do, I'm going to get 1 over 0 plus 3 minus 1/3 over 0. That's the wonderful 0 divided by 0. Means there's more work to be done to find our answer. So I will tell you, whenever you're dealing with a compound fraction like this, what you want to do is look for a common denominator. So I'm going to deal just with the numerator right now. What value is our common denominator? And the easiest way to do it is to multiply these two together. So if I multiply this side by 3 over 3, and multiply this side by x plus 3 over x plus 3, you'll find that I'll get this, 3 over 3 times x plus 3 minus 1 times x plus 3, which is x plus 3, over that common denominator, 3 times x plus 3. Now some people multiply this out and do 3x plus 9. I always want to see what cancels out a lot, so I don't tend to multiply through until the end, if necessary. All right, so what happens here? Well, here very nicely, three minus the quantity x plus 3. Over the common denominator, all over x. So 3 minus x, the quantity x minus 3, this 3 and this 3 will subtract away. We're going to end up with negative x over 3 times x plus 3 over x. Now I'm going to put that over 1 for a nice compound fraction. And if you recall, when you have compound fractions, numerators will divide away. Numerators will cancel each other. Denominators will cancel each other. So this x and this x actually will cancel each other out. You'll be left with, don't forget your negative, negative 1 over 3x plus 3. And this will be 1 on the bottom. So it's all divided by 1. So here's your simplified expression. Now, the danger has been removed that x was taken out. X was making the problem. If you plug in 0 for x, you get 0 over 0. That was the issue. Here, we don't worry about it. We're gone now. If I plug in 0 for x, I get negative 1 over 3, 0 plus 3, which is 3. 3 times 3 is 9. So my answer is negative 1/9. Okay, a lot of work on that, a lot of algebra to that, but that's one of the ways we find a limit. Whenever you have 0 divided by 0, that means there's something we can do. Like in this case, if I plug in 0, 1 minus the cosine of, well, cosine of 0 is 1, and 1 squared is 1, so it'd be 0 over 0. Means there's more work to be done. So there are a couple ways to do this problem. I'm going to do it 2 ways. The first way, and I want you to see if you remember this. This is not something that is easily remembered, I suppose. It's a little of a identity that is always true. When x goes to 0, the limit of x going to 0, sine x over x is 1. All right, that was hopefully shown to you in the beginning of the school year. If not, I'm telling you now, that's true. The reason that's important to us is this. If you remember also from last year, you did this in pre-calc probably quite a bit. Oh, I should put x's, sorry. Remember that sine squared plus cosine squared equaled 1? So if I subtract cosine squared from each side, this thing here is really sine squared of x. Now, how does that help us in this problem? Well, remember, keep these two things in mind. We're going to do it. So I'm going to break this up into sine x times sine x, because that's what it means. That's what sine squared means. Okay? So I'm going to write this and see if you guys are with me on this one. I just decided to multiply sine x times sine x over x. Now here's the thing, right there. What is the sine x over x equal to? Well, it's equal to 1. And what's sine x over 1 equal to? If I plug in 0, what's the sine of 0? Well, it's 0, and 0 divided by 1 is 0. So I end up with a limit of 0. Okay? That's one way to do the problem. I'm going to duplicate this page and do it a second way. Second way that may be easier. Okay? Because here you're going to use something called Hopitals Rule. Now, Hopitals Rule is a rule that follows a pattern of the ratio of a limit is equal to the ratio of its derivative. Here's what I mean. If I have a limit as x approaches some number, doesn't even matter what, of two functions that are being divided, okay, as long as you get the form 0 divided by 0 or infinity divided by infinity, this is true. Their derivatives have the same limit. Okay? Now, as we saw in the last time we did this problem, when I plug in 0, I get 0 over 0, which means I can use L'Hopitals rule. So let's do it. What's just a derivative at the top and bottom separately, not together? It's not quotient rule. It's separately. What's the derivative of 1? 0. Minus. What's the derivative of cosine squared of x? Remember, cosine squared of x really just means it's cosine of x squared. So the derivative is, we drop the 2 in front. And then what's the derivative of the inside? What's the derivative of cosine? Well, it's negative sine. That's the top. And what's the derivative of x? 1. Well, we've eliminated the danger. We're not going to have 0 on the bottom anymore. That's good. Now let's plug in 0 and see what we get. 0 means nothing. What's the cosine of 0? Oh, it's 1. But what's the sine of 0? It's 0. So the top, 0 times 1 times negative 2, is 0. Okay, so it's two ways to do that problem. They're both equally valid. I think you'll find that L'Hopitals rule ends up being a little bit easier in the long term because there's not much manipulation you have to do. You just flat out take the derivative and then look at the derivative. And I'll tell you what, if the derivative still yields 0 divided by 0, or infinity divided by infinity, take the next derivative. Keep going until you come up with an answer. All right, that's L'Hopitals rule. Now this here, you may or may not remember, is the definition of a derivative. But I'm going to show you, let's just figure this out. It's actually a very easy problem to do algebraically. Most people do not like delta x because it's a cumbersome variable. So we change it to something else. So you probably learned h. And h is just the distance between x and the next part, which is what the delta x stands for. It doesn't matter. It doesn't matter what it means. I'm just putting h instead of delta x to make the manipulation of the algebra easier. Now if I plug in 0, I'm plugging in 0 for h. I'm going to get x squared minus x squared over 0. So that means I can do some work. All right, let's multiply this out. So let me square that binomial. Remember the x squared, multiply and double, square the last. Now this will happen every time you have to do something algebraic of a 0 over 0. Something will cancel out because it has to. X squared minus x squared is 0. It's gone. What I have left has an h term in it. So I'm going to factor out that h. Which now means those h's will cancel out. So my denominator is gone. Well, it's not gone. It became 1, so it's not a danger anymore. Now if I plug in 0 for h, I get 2x. Now bonus points. If anybody happened to remember that this was the definition of a derivative, you would know that x squared is the function. And what's the derivative of x squared? 2x. So if you recognize that, would it have been faster? Sure it would, but that's okay. All right, continuity. Do you remember the 3 conditions for continuity? Condition number 1. You have to assume that the point exists on a function. If the point exists, it could be continuous. If it doesn't exist, it's not continuous. So the 3 conditions have to be met. Here's one. The function has to exist. Thing 2. the limit has to exist. So a function has to exist and a limit has to exist. And the third thing was the point and the limit had to be the same. So let's look at these two discontinuity points and let's figure out which of these conditions make it non-continuous. So it's not continuous at -3. It's got a hole. Well, you could say, oh, it's got a hole in it, but really, what's the actual reason? F of 3, or f of -3, does not exist. Let's do it with a capital G. Does not exist. You don't even have to worry about finding a limit or anything because guess what? It doesn't exist. Now, how about 5? The point exists, so let's go on to the next one. Oh, look, the next one, the limit doesn't exist. From this direction, it's, what's it, 1, 2, 3, 4, 5. So from this direction, the limit's 5. From this direction, the limit is 1. Well, if a graph is going to two different places and two different sides, then the function doesn't exist. So the limit, as x approaches 5, of this function does not exist. Those are the actual definitions for limits. Now, or for continuity, I'm sorry. Now let me give you an example of this third one, because it looks a little bit weird. So come back to this point here. Let's just say that I put a point here. So my question to you would be, at, what's that, -3, does the function exist? Yeah, it exists. It's right here. F of -3 is 1. Does the limit exist? Sure enough, from both directions, aren't I going to the same point? That point happens to be -1. So the point equals 1. The limit equals -1. So then the third condition is not met. If those two aren't the same point, it's not continuous, which it's not, because 1 does not equal -1. So that's an example of the third reason. Okay. But those are your formal definitions for continuity. And we can kind of use that idea here. We have a piecewise graph. We have c minus x. So it's a linear equation. That's a slope of -1, and it starts at some value c. After pi, it becomes the trigonometric function. So what we have is we have a straight line, and we have a trig function. And the question is, I didn't mean to connect them. Let me try that again. So the question is there a value where these things connect? Because we know a sine function is continuous. We know a straight line is continuous. The only danger is, do they connect? If they connect, it's continuous. If they don't connect, it's not continuous. So we got to figure out what makes those continuous. So here we go. I know that c minus x has to equal c times sine of x. These two functions have to be the same value. At what point? Where our only point of danger is pi. Because everything less than pi, we go with this. Everything greater than pi, we go with this. So when it equals pi itself, do they connect? So let's plug in pi for x. All right. Do you remember the sign of pi? It is 0. Our sine of 0 is 0, and pi is 180, so it's another 0. So that means c equals pi. So if c equals pi, the function is continuous. Okay? And it's pretty easy to check. If I plug in pi, it's pi minus x. Well, if I plug in pi for x, I get pi minus pi, I get 0. If I plug in pi here, sine of pi is 0. So both these values equal 0. So technically, this graph looks something like this, although it's not necessarily perfectly accurate. But something like that. And here is 0, 0, I'm sorry, is where they connect. Okay. At pi 0. All right. Almost done. Thanks for hanging in with me. I appreciate it. Number 11 here. Determine vertical and horizontal asymptotes. Verticals are pretty easy. You got to find out, you got to make sure the denominator doesn't equal 0. Well, you know in this case, x minus 4, x plus 4. It doesn't really matter that it's under the radical because nothing would cancel with the numerator anyway. So what two values make this make the denominator equal to 0? Well, you got negative 4 and you got positive 4. Those are your two vertical asymptotes because that's what makes the denominator equal to 0. All right, now the horizontal asymptotes are flat. What happens when it goes on forever? So what happens when x approaches infinity? Now I'm going to talk to you about the intuitive way to think about infinity. My first thing I'm going to say to you is, if I'm going out to positive infinity, billions and trillions and zillions and Googles and Googleplexes and all that, will adding a 5 or subtracting a 16 make any difference whatsoever? I mean, what's the difference between a billion and 5 divided by a billion minus 16? Not much. So when I think about infinities, I realize these two things don't really make anything. So in the long run, these are the only two things that matter. They win a war with those. Now, will one of these two win a war with each other? Well, x is x. What's the square root of x squared? Oh, it's x. So guess what? They don't win a war, they tie. X divided by x is 1. So your horizontal asymptote is 1. Now that's when x goes to infinity. What happens if it goes to negative infinity? Now all this works. It's all the same. It's going to go to 1, except be careful of signs. So pick a negative number, any negative number you want. Negative 20. If I plug in negative 20, this top becomes negative 20. But if I plug in negative 20 here, negative 20 squared is going to be 400. And the square root of 400 is 20. So just be careful. When I go to negative infinity, I get an answer of negative 1. Now, if you take a look at a graph or a table, you're just going to find that when this graph goes this way, it's going to flatten out at negative 1. And when it goes this way, it's going to flatten out at 1. It's just the way it's going to be. Because that's what happens out to infinity. It seems weird. How can I just ignore these two numbers? Because it doesn't matter. It doesn't matter. Okay? All right. The intermediate value theorem, that sometimes we call IVT for short. And if you don't remember it exactly, you know what it does, because once you see this, if I have a point here and a point here, and I've got a continuous function of some kind. So if I have a positive value and a negative value, that means at some point during this graph has to hit every point that's between this and this. So say this is 3 and this is 3, negative 3. Let's just say that. So to go from 3 to negative 3, I have to hit every point between 3 and negative 3. Now this one's asking us specifically about a root on this interval. So all you got to do is test the endpoints. If I plug in 0, I get negative 6. If I plug in 3, I get, what, 27. Plug in 3 minus 9 plus 3 minus 6, which would give me, what, 15, I think? So to go from negative 6 to 15, guess what? It has to pass 0. And this is all you have to show. Then you can say that by the intermediate value theorem, there is a root. And a root is where just x equals 0 on the interval 0 to 3. Okay. That's the IVT, intermediate value theorem. All right, what do we got here? Discontinuities. So the only time something is discontinuous is if the denominator equals 0. So I'm going to factor that. So my two trouble spots, I have discontinuities. Is that spelled right? Discontinuities, yeah. At negative 2 and 2. Now it also asked about removable or non-removable. So could you cancel out these x minus 2's? You could. So technically, we've removed it. So we have, whoops, I can't spell. We have a removable discontinuity at, and which one did we remove? We removed the x minus 2. So what value would make that 0? It would be 2. We removed the 2. That was the removable discontinuity, which means negative 2 is not removable. All right. Good job. Thanks for hanging in there. Last one. The answers will vary on this, but you know, there's just a bunch of ways to do it. But things to keep in mind. The limit as x goes to infinity equals 1. So here's 1. So that means that whatever's going to happen, he's going to flatten out at 1. I don't know if it's coming from the bottom, coming from the top, going through, but anyway, but it's all going to go out to be 1 to infinity. All right, for negative infinity, it's going to be negative 2. So when we go this direction, it's going to flatten out along this line. Again, I don't know how or where, top or bottom, but it's going to do it. I know that the limit as x approaches negative 2 from the negative side. So from the right side? From the left side. So bad with that. From the negative side. Negative 2 from the negative side. That the limit is going to be 3. So here's negative 2, 1, 2, 3. So that means it's going to equal some point. Now, can it be a hole? Sure. Can it be a solid point? Sure. We don't know what it is. We just know that it's got to go through that point. So this is all I know about this side. So I'm just going to make it flatten out. This is going to be my graph so far. So I've got this. I've got this. Now a jump discontinuity at negative 1. So a jump means that it goes from one place to another place. So let's just say this keeps on connecting through. And then it's got to start here and go somewhere, up or down, I don't know. But that's your jump discontinuity. Now an infinite discontinuity at 0. All right, that means it's either shooting up to infinity or it's shooting down towards negative infinity. It doesn't matter which one. I did up because it was closer and easier to draw. And what about the other side? So the other side is also going to come from infinity, or it can come from negative infinity. It doesn't matter which side. So I think because my vertical asymptote is here, or horizontal asymptote is here, I'm just going to have it come from the top. Removable at 1. So at 1, you've got another 1 like at negative 1. We have removable 1. So let's say it's going to there. Stops, it's removed. Now could it continue on? It could. Could it jump? It could. But a removable 1 means we just took it out. It didn't actually, it's still continuous there. It still goes through it. And could there be a point somewhere else? Could the point be up here? Sure it could. Could the point not exist? Yeah, we don't know about the point. We just know that there's a hole in the graph. And the last thing, well, actually I haven't flattened this out to 1 yet, but we will. But the last one is a cusp. Now, cusp means a point. So if you have absolute value, that's your cusp. And a cusp basically means you don't have a derivative. Okay, you can't instantly change from a negative to a positive slope. So there's a cusp at 2. So we can do the cusp anywhere we want. We could say that it, boom, hits a V, but now it's got to come and flatten out here. So that's a possibility. We could have drawn it underneath and bumped it and put it back up. It doesn't matter. We don't know what it does out here, but we don't care. Now, have we hit all these criteria? Yes. Is this one possible graph of many? Yes. But just make sure you understand how these are affecting the graph. I do not foresee any AP test question where you're going to be drawing a graph because frankly there's not enough time. But there are many times you could be asked to interpret a graph. So it's good to know what those things are. Anyway, that is the review. If you have any questions, let me know. And good luck to you. Bye.